Our next presenter is Mr. Gregory Wilkie. He's a project associate at the WSP Group, Washington, D.C., specializing in building enclosures. Mr. Wilkie's passion for design technology speaks to his experience in building simulation and its use for guiding the detail and fabrication of building components. This experience, as applied beyond concept development, has broadened his knowledge-based construction and understanding of the path from idea to product. Mr. Wilkie incorporates sustainable design ideas through discovery and definition, climate and place, load reduction, integrated solutions, renewable systems and occupancy, which close the gap between concept designs and best optimum design iteration. Social practice is also a feature of Mr. Wilkie's work. He is a co-founder of Make DC, Washington, D.C.'s first public interest design studio that focuses on people. Their designs contain socially and environmentally responsible initiatives helping everyday people with everyday problems. Gregory's presentation is called Macro to Micro, Striving for Energy-Efficient Homes Through Re-Engineered Clay Blocks. Gregory?
Good afternoon, thank you. Macro to micro. I always had a feel for designing from large scale to small scales and working back and forth. So this research focused a lot in process. So it's really process driven, and how you have an idea, you see the overall scale, you go down to a unit, and then you kind of keep recycling that process over until you tweak in different criterias. So just to give you a quick outline of what is going to be talked about, we looked at references over the course of Trinidad and Tobago in terms of the housing. We looked at the climate influence. Also, we looked at the concrete block versus the clay block. And then clay block production, we spent a little time looking at the processes within the clay block production. And then we dived into the exploration of how you design those criteria per that idea, and then looking at the outcome again, and then reprocessing that information. So looking at the technical and cultural data, we looked at the different images of housing around Trinidad and Tobago, just to gauge an idea of what's happening within the built environment, the idea of your gable and hip roofs, throughout the design, and then the simple forms of a rectangle, some of them typically 30 by 30 square feet square. And then looking at the climate in terms of where you have most of your solar exposure, most of your wind-driven rain, wind directions, and then your temperature and rainfall amounts throughout the course of a year. Looking at some of the influences from our past and how we designed before. So the idea of large openings, raised floors, fixed louvers, and all these adaptable design features that were used to keep the building cool on the inside. So from that, we overlay that into different types of section. And in doing this, we kind of picked up the types of materials we'll use over the course of time. So coming from like the Amerindians all the way up to now, in terms of using thatch roofs for the rooftops or sticks, the use of clay blocks and timber floors, and then the use of concrete blocks, reinforced concrete, and you have your rooftops, Z-pillars and zinc roofs. So mapping the material types over the course of time period of history, we looked at that in terms of before Industrial Revolution and after Industrial Revolution. And with that, you overlay the same materials you have over time that was developed. And with that, you kind of see the overlap of some of the materials used before Industrial Revolution and after, being that you found that clay popped up a lot over the course of our history, which means there was a pretty good understanding of how that material worked in our climate. So with that, I kind of focused the research more on concrete versus clay. So we looked at the traditional 6-inch blocks. You look at the concrete block, and this analysis was kind of run using Energy Plus. So we ran energy models in terms of how these blocks perform given heat gain to the interior spaces in both comparison of the clay versus the concrete. So with that, you looked at the typical layout of the house walls, and you looked at the concrete block, which is on your right, and the clay block, which is on the left, and you looked at the breakdown of the heat gain to the interiors in those graphs to the bottom left and right over the course of a year. So you find, obviously the roof, of course, was the most heat gain, as discussed earlier in some of the presentations we saw. You have your window, and then you have your doors, and then the walls. But seeing that we had control of this unit size form of a block, we started focusing on the analysis or this development of change with the block. So with that, we looked at also the roof types, just a minimal change on the roof types. You have your typical your gable roof, and you have your hip roof you see that is commonly used across the country. So if you were to take that gable roof and rotate it 90 degrees and then rotate it 45 degrees, you see the difference in terms of the heat gain to the interiors over the course of a year. As it decreases, and then you have the square hip roof, which kind of reduced the wall, which of course is less surface area on the wall of that. So obviously the wall consumption to heat gain was reduced drastically. But you had the issue of where it increased on the windows and the roof. So with the model moving forward, we started using the hip roof as our baseline model. So every scenario from henceforth must do better than that of 284 kBTUs over the course of a year. So in understanding the clay block, we looked at the process as well. Where could we inject certain aspects within the production process that is simple and probably minimal that could create change? So you understand in terms of the process of clay, you have the sourcing of the material, cleaning it, then you have the mixture and then extruding it. You had the wire cutter process, and then you had the dryer and then to the kiln. So just understand those processes where we could introduce some of that in the new design. So the exploration focused more on the idea of reducing energy consumption and harvesting rainwater as well. You want to capitalize on the performance and still achieving that aesthetic quality. And then how do you inject certain things throughout the manufacturing process that is minimal and still relate to that social, environmental, and financial characteristics, therefore creating that triple bottom line. So performance criteria. The block which we focused on the wall had these criteria designed. You're either doing heat gain or you're doing water runoff when you talk about a wall surface. So the heat gain is divided into two types. Either you're doing shading, which is either on the south side, so it's very specific to orientation, which is either horizontal shadings you use typically on the southern side. On the western side, you have vertical shading or self-shading devices. Then you have insulation, which cut down the amount of heat getting to the interiors, which is a secondary material. Then you have the water runoff, which is dependent on the angle on the surface, cavity on the surface, or texture. So first start off, we go into the horizontal shading. What kind of blocks you could design just quickly and come up with some concepts. So this column shows the idea of the design together with the analysis that was run with it. So we design a block, and then at that point, you run a shading analysis on that block to see how much self-shading happens on the blocks, which means less heat is getting onto the block at that point if it's being self-shaded. Then we move on to the vertical shading as well, same process. You run the shading analysis, study on it, and then rank those given the percentage of shading on the block. This was done on a typical 1 meter square part of the wall, and then the analysis was rerun continuously. Insulation. So the insulation was done either by adding multiple cavities. The typical block, you normally see 2 cavities. So how do you add multiple cavities within the block to create or slow down heat gain to the interiors? And also probably using insulation in some of the cavities you use. That was explored together with finishing the outer surface of the block with a ceramic finish like you do with tiles, which is the heating process is much stronger. Then we looked at layers again, insulation layers, and again that same reflective surface I just talked about in terms of the ceramic. And these again were rerun within Energy Plus of the model again, and those values were obtained for the different orientation. Looking at water runoff, we designed doing the angles. So how do you create angles on the exterior surface of the block to prevent water from both, or efficiently moving water off the surface of the wall? That again was run, and then the percentage of water runoff was given in terms of the criteria. Put cavities on the block on the exterior as well. How do you channel water out using cavities? And then textures, different types of textures. So with that, our outcome from those designs, we kind of slim it down using the initial baseline we had from the beginning, where you had the 284 kBTU of the hip roof. So we wanted to make sure that our blocks are performing better than that. The shade must be greater than that, of 50% of the block must be shade in itself. We wanted to maintain the structural cavity, which was meant in the original blocks. So you had to have at least a minimum of 2 cavities in the design block. And we tried to consider construction process. So the idea of not having a secondary material for insulation was excluded at this point. If you needed it, it could be added in. And then in terms of material, a concrete block has about approximately 400 cubic feet of material. So anything using less material, we would have go forward with the design. So with that now, the blocks were rerun and sorted per these performances. As you can see on the far left side of your screen, that the blocks were now organized as the top 2 blocks in that category. So it was done for the horizontal, it was done for the vertical types, it was done for the insulation, and then it was done both for reflective, and then you looked at the water surface blocks. So with that water runoff, none made it out of the cavity type, and neither the texture type. So with that, these were the blocks that were finalized in terms of the design from that rerun of process. So you can see in this block here, this became the standard new clay block, which then had 4 cores. One block was a typical 6-inch. If you were to break the block like this one here, you see here, you'd end up with a 4-inch block. And you had also the option of putting insulation within the block to prevent solar heat gain to the interiors. And we run the numbers both with insulation and without insulation, and they still perform much better than that of the existing clay block. We looked at the shading block with the horizontal grooves on it for the southern exposure. We looked at the western side for vertical exposure of the block, and then these 2 surface cut angles that were developed for the north and the eastern side of the block, so that water could efficiently run off the block if it was hidden from the wind-driven rain of the northeast. So with that understanding, now we went into the actual process. How does this now influence the production of this block? So we kind of diagrammed the ideas of the block. You could see highlighted in the green is the different processes of those additions. The far right would be addition to the process that currently exists. So this block, to do the process, no addition to the production line. We looked at the vertical west self-shading block. Again, it's just a matter of putting on a new extrusion plate to the front, which would give you that finish, so you don't need additional process. And then southern, On the sudden exposure now, you realize you added one additional step in a second wire cutter. Not only you were cutting the blocks into the sizes you need, but you were also removing material from the front of the exterior face. So that was an additional process in the development. And the same thing applied to the north and eastern block as well, in which you would have a support that actually held it in place, and then you applied a secondary wire cutter as well. So how does this fit into the built environment? So you look at the existing conditions. How do we now look at this block as it develops and then it grows over time? So we look at a simple context of where you have the north, the street running east-west, and you have your walls really facing north and south as well on the street level. So with that and the blocks we just came up with, we started running that again through the energy process again. How does this perform during the energy process? So we started stacking the blocks on all the surfaces of that orientation. So if you were on the south facade, that entire wall would take the block type. And then we run the energy model to see the outcome. We did it to half the point, which was just under the sill, and rerun the model again. And then thirdly, we started staggering it below the sill, moving its way up. From there, we realized in terms of costs and the returns in terms of the energy you were gaining, the heat gain into the interiors wasn't that much for you to actually do the entire wall. And the bottom part too of staggering it, it was kind of losing that much of 200. So we started saying, okay, this block would be designed to use just up till the underside of the sill. At that point, the roof was doing the rest in terms of shading, so you didn't need to continue the performance. So you looked at it in the built environment again, kind of how it looks, how it behaves. Same thing was done again for the north and eastern side block type. And again, you didn't need to do the entire wall again or stagger it. So again, in ease of construction, it was just built to the underside of the sill. And again, you look at the idea in terms of the built environment and see the idea of how over time the block more started growing on it. It started aging over time and adapting. And again, it was rerun for the west facade as well. And the same option was selected. Looked at it in the built environment and the context. So from there, we did a run of the cost analysis of the 6-inch concrete block versus the 6-inch clay block. With that, we kept everything standard because the house type was pretty much the same. The ring beam used to have the same cost ring beam on the top. The windows, doors, same type, symbol doors. Foundation would be the same. The cost for a hip versus a gable is about the same, just more time consuming. And we looked at the clay block cost. The new clay block cost went up by a little bit in terms of costs, which was adding an additional $742 to the cost of the house. When you rerun that now, when you did your energy costs analysis in terms of your annual consumption for the year, you realized from the concrete to the clay, you're saving $497 a year. With that, and with the new cost of the block, you were paying that back within a year and a half, pretty much. And with that, you're always saving energy consumptions from thenceforth. So with that, in terms of the analysis, we realized that in that understanding, we move into and how do you treat the window at that point, this opening that you have within the wall. So understanding that process and how we develop that system in that reiteration for the concrete, the clay block, how do you now apply that process to the window and now develop a new window system for that of Trinidad and Tobago? Thank you.
Thank you, Gregory. Do we have any questions for Gregory on that topic?
Gregory, has there been any luck with the local manufacturers in accepting this technology that you have quite well articulated it?
Well, in the early discussions I talked to Abel a lot in understanding the production process and how clay behaves in terms of the limitations on how you could actually remove material. But no, I haven't had any conversation after that in how they're moving forward. I think they're very nervous about adding a new production mechanism within their current line that they know works. But no conversation has been developed since the design has been this stage.
George Simon. One of the things that concerns me about putting a pattern, whatever pattern it is on the block, it's going to require more cleaning. You're going to get cobwebs inside those grooves, you're going to get dust collecting and so on. Have you factored in the cultural aspect, the cultural acceptability of a block that would require much more cleaning effort? Ladies in Trinidad like to see the house clean.
That's a very good question. I would say no, I haven't factored in the maintenance factor of that part. But like any new technology now, there's always a learning curve in how the step moving forward. A learning curve in educating how to use new tools. So the idea of now transitioning that idea of sustainability moving forward, there will always be a learning curve in how to do that. And I think this is one of these processes you'll have to go through.
Atlantic Energy. Gregory, that was a fantastic presentation. Congratulations on that research. What I want to find out, in terms of the production process upstream and the minor changes you did you transfer the energy cost upstream? Or did you transfer any additional energy cost upstream to produce
the block?
Yeah.
No energy was discussed during the clay block production, but judging by the cost of the production, in terms of adding additional wire cutter, from talking to Abel, it seems like it's not that much of a cost to add a wire cutter. If you're talking additional extrusion or increase in firing systems, then yes. But the fact that you had to just do a wire cutter, it wasn't that of a big of an increase to throw off your cost benefit.
It seems as though most of the analysis was done with respect to the heating and the energy savings. But was anything done to ensure that the structural strength of the block matched what you had before? And also some of the designs, I think particularly the shaded one, looks a little bit fragile in a sense.
Right. So the structure was designed to maintain the cavity, which you could, as other clay blocks, you reinforce with steel and fill with concrete. And that additional third and fourth core is where you will use an insulation or air to slow down the heat gain to the interiors. So with that, you still maintain that structural integrity of the block without actually losing the performance.
Gregory, since Dr. Sami drilled me, I'll take my turn as you. I didn't really understand the rainwater harvesting in terms of, I'm seeing angled blocks, but where is the water collected in the blocks or in a cistern below?
So, yeah, what the block was designed to do is to move the water away from the typical mortar lines and get it down. So a re-engineered part of the slab had a grill. So like it had a drainage system on the north and eastern side which collected the water and then put it in a cistern.
Untitled Chapter. Could you elaborate on the effect of the number of cores in the block? Was there any correlation between the number of cores in the block? Because some time ago, not ABEL, but Trinidad Aggregate Products was promoting a 6-core column block, and I was wondering if there was anything to be gained by increasing the number of cores.
So far in the research I did, there's no intent. If you increase the amount of cavities in the block, it doesn't hinder the strength of the block. The only thing is that in terms of energy performance, after you cross 4 cores, the minimal energy returns you get in is not necessary. So I didn't need to increase past 4.
Okay, we must say thank you very much to Gregory. You've generated a lot of interest in this topic. Yes.